Before we begin, take a moment to settle in. This video is accompanied by gentle background tones tuned to 432 Hz, 528 Hz, and 741 Hz, carefully layered to support deep relaxation, calm focus, and a smooth transition into sleep. You do not need to pay attention to them. Simply allow the sound to exist around you. Tonight's journey is not rushed. There is nowhere you need to go, and nothing you need to remember. The topic of this video is what existed before the Big Bang. For most of our lives, we are taught that the universe began with a single explosive moment. A beginning of time, a beginning of space, a beginning of everything. But here is the quiet question that refuses to disappear. If the Big Bang was the beginning of the universe as we know it, what was there before it? Not chaos, not nothing, not necessarily a sudden explosion in empty darkness. Modern physics suggests something far more subtle, far more mysterious, and far more difficult to imagine. Right now, as you lie still, your body feels at rest. Yet the Earth is spinning beneath you. The planet is orbiting the sun. The sun is moving through the galaxy. And the galaxy itself is drifting through an expanding cosmos. Everything is in motion. And yet, this story begins in a place where even time may not have existed yet. In this video, we will slowly explore the theories scientists and cosmologists have proposed to describe what may have existed before the Big Bang, not as absolute answers, but as calm possibilities. Cycles, quantum states, eternal fields, silent dimensions, and universes that breathe in and out over unimaginable spans of time. There will be no sudden sounds here, no urgency, no need to stay awake. You can listen actively, or you can let the words pass through you as you drift toward sleep. Because some questions are not meant to be solved tonight. They are meant to gently carry the mind away from the present moment. So take a slow breath, let your shoulders soften, and allow yourself to drift backward in time, beyond stars, beyond space, beyond beginnings, to the quiet question that came before everything. Close your eyes for a moment and imagine the deepest darkness you can conceive. Not the darkness of a moonless night, nor the darkness of a cave buried beneath mountains. Imagine instead the absence of all things. No light, because there are no stars. No space, because there is no distance. No time, because there are no moments to follow one another. This is the realm we seek to explore together, the mystery that rests at the very foundation of existence itself. The question of what came before the Big Bang is perhaps the most profound inquiry human minds have ever formulated. It sits at the intersection of physics and philosophy, mathematics and imagination, knowledge and wonder. And yet, even as we ask this question, we must pause to consider its very structure. What does it mean to say before when we're discussing the potential origin of time itself? Can there be a before if time had a beginning? Can the word before have any meaning in such a context? These are not mere word games or philosophical puzzles to dismiss. They are genuine challenges that reveal how our everyday language and intuitions, shaped by our experience of living within time and space, may be inadequate tools for grasping the true nature of cosmic origins. We are creatures who exist in time, who remember the past and anticipate the future, and so we naturally think in terms of befores and afters, causes and effects. But the universe at its most fundamental level may not operate according to these familiar categories. Throughout this exploration, we will encounter ideas that challenge our basic assumptions about reality. We will meet theories that suggest time itself is an illusion, or that our universe is just one bubble in an eternal ocean of universes, or that what we call the Big Bang was not a beginning at all, but merely a transition from some previous state. Some of these ideas are supported by sophisticated mathematics and have been developed by the brightest minds in physics. Others are more speculative, existing at the frontier where science touches the unknown. Our journey will be gentle and unhurried. There is no race to reach conclusions, no urgency to solve mysteries that have puzzled humanity for millennia. Instead, we will move slowly through these cosmic landscapes, pausing to appreciate the beauty of each idea, the elegance of each theory, the wonder of what we know, and the even greater wonder of what we do not. Think of this exploration as a meditation on existence itself. As we consider what might have existed before the Big Bang, or whether that question even makes sense, we are really asking about the deepest nature of reality. We are asking why there is something rather than nothing. We are asking what the fundamental laws of nature are, and whether they themselves require explanation. We are asking questions that may not have answers, at least not answers we can currently comprehend, and learning to be at peace with that uncertainty. The scientific theories we will explore are diverse and sometimes contradictory. Some propose that the universe had no beginning, that it has existed eternally in one form or another. Others suggest that time itself emerged from a timeless quantum state, so that asking what came before is like asking what lies north of the North Pole. Still others envision our Big Bang as just one event in an endless cycle of cosmic expansion and contraction, death and rebirth. What unites these various approaches is a willingness to follow the mathematics and the logic wherever they lead, even into realms that seem utterly alien to our everyday experience. Physicists and cosmologists working on these questions are not engaged in idle speculation. They are using the most powerful tools humanity has developed, the languages of mathematics and physics, to probe the limits of what can be known about our universe and its origins. At the same time, we must acknowledge the fundamental limitations we face. There may be aspects of reality that are simply beyond our capacity to observe or measure. The very earliest moments of the universe, if such moments existed, unfolded under conditions so extreme that we cannot recreate them in our laboratories. The energies involved dwarf anything we can produce. The temperatures were higher than anything we can achieve. The densities were greater than anything we can imagine. We are like detectives trying to solve a case where most of the evidence has been destroyed, working with only the faintest traces and clues. And yet, remarkably, we are not completely in the dark. The universe has left us messages, written in the cosmic microwave background radiation that fills all of space, encoded in the distribution of galaxies, hidden in the mathematics of quantum mechanics and general relativity. By reading these messages carefully, by following the logical implications of our best theories, we can begin to sketch out possibilities for what might have existed before the Big Bang, or what the concept of before the Big Bang might actually mean. As we embark on this journey together, let go of any need for certainty or complete understanding. The questions we are exploring have occupied some of the greatest scientific minds of our time, and they remain open questions. Our goal is not to arrive at definitive answers, but to appreciate the profound mystery of existence, to marvel at the universe's capacity to surprise us, and to find a sense of peace in contemplating these deep questions. Let your breathing slow and deepen. Feel yourself settling into a state of relaxed curiosity. We are about to explore ideas that stretch across billions of years and potentially infinite space, concepts that challenge the very foundations of how we think about reality. And we will do so gently, thoughtfully, with the calm awareness that comes from knowing we are part of this great cosmic story, even if we cannot yet understand all of its chapters. The darkness before the Big Bang, if such darkness existed, is not something to fear. It is a mystery to contemplate, a puzzle to appreciate, a reminder of how much wonder still exists in our universe. So let us begin our exploration, moving slowly and carefully through the landscape of ideas that modern physics and cosmology have given us, always remembering that the journey itself is as valuable as any destination we might reach. Before we can truly grapple with the question of what existed before the Big Bang, we must first understand what we mean by time itself. This may seem like a simple matter. After all, we all experience time every moment of our lives. We watch the clock tick forward, we age, we remember yesterday and plan for tomorrow. Time feels like the most fundamental and obvious aspect of reality. But when we look closely, time becomes strange and elusive, more mysterious than we might have imagined. In our everyday experience, time seems to flow like a river, carrying us inexorably from past to future. We feel that the present moment is somehow special, somehow more real than the past that is gone or the future that is yet to arrive. This intuitive sense of time is deeply embedded in our consciousness and in our language. We speak of time passing, of events happening in sequence, of the arrow of time pointing from before to after. But physics tells a different story. In Isaac Newton's classical physics, time was imagined as absolute and universal, a cosmic clock ticking away the same for everyone everywhere in the universe. Whether you were on Earth or on a distant star, whether you were moving or standing still, Newton's time flowed at the same steady rate. This notion of absolute time seemed to match our intuitions perfectly. Time was the stage on which the universe played out its drama, a backdrop that existed independently of the events occurring within it. Then came Albert Einstein, and everything changed. Einstein's special theory of relativity, published in 1905, revealed that time is not absolute at all. Instead, time is relative. It flows at different rates depending on how fast you are moving. An astronaut traveling at a significant fraction of the speed of light would find that their clock runs slower compared to clocks on Earth. This is not an illusion or a trick of measurement. Time itself genuinely passes more slowly for the moving astronaut. If they traveled far enough and fast enough, they could return to Earth to find that only a few years had passed for them while decades or even centuries had elapsed on Earth. Even more remarkably, Einstein's general theory of relativity, published in 1915, showed that time is not separate from space. Instead, space and time are woven together into a single four-dimensional fabric called spacetime. Matter and energy curve this space-time fabric, and this curvature is what we experience as gravity. Near a massive object like a black hole, space-time is curved so severely that time itself slows down dramatically. Close to the event horizon of a black hole, time crawls to a near stop relative to observers far away. These discoveries force us to rethink what time really is. Time is not a backdrop or a stage. It is part of the universe itself, inseparable from space, affected by matter and energy, variable rather than absolute. When cosmologists speak of the Big Bang as the beginning of time, they mean something quite literal. According to general relativity, space-time itself came into being with the Big Bang. Before that moment, if we can even use the word before, there was no space-time and therefore no time. This is where the question, what existed before the Big Bang, becomes genuinely problematic. It is not that we do not know the answer. It is that the question itself may be based on a misunderstanding. If time began with the Big Bang, then there was no before. The Big Bang was not an event that happened at a particular moment in a pre-existing time. It was the origin of moments themselves, the beginning of the sequence we call temporal order. To understand this better, consider a useful analogy often employed by physicists. Imagine asking, what lies north of the North Pole? The question seems to make grammatical sense, but it has no answer. North is a direction defined relative to Earth's geography. The North Pole is the northernmost point. There is nowhere that lies north of it, not because we have not looked carefully enough or traveled far enough, but because the question asks for something that is logically impossible within the framework that defines north and south. Similarly, asking what came before the Big Bang may be asking for something logically impossible within the framework of time as we understand it. If time is part of the universe, and if the universe began with the Big Bang, then time began too. Asking what happened before time began is like asking what lies north of the North Pole. The question assumes the existence of something, a temporal sequence, that may not exist. And yet, this answer may feel unsatisfying. Our minds rebel against the idea of an absolute beginning. We want to know what caused the Big Bang, what set it in motion, what the initial conditions were. These are natural questions, arising from our deep-seated intuition that everything has a cause, that nothing comes from nothing, that there must be an explanation for why the universe exists at all. Modern physics offers several ways to think about these questions, and they do not all require us to abandon the notion of before entirely. Some theories propose that time as we know it emerged from a more fundamental, timeless reality. Others suggest that time is eternal but changes its character, so that before the Big Bang there was a different kind of time, perhaps imaginary time in a mathematical sense, or perhaps time in a universe with different properties than our own. Quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, adds yet another layer of strangeness to our understanding of time. In the quantum realm, the clear-cut distinction between past, present, and future becomes blurred. Particles can exist in superpositions of states, being in multiple configurations simultaneously until they are observed. Quantum effects can appear to reach backward in time, influencing earlier events. Some interpretations of quantum mechanics suggest that time itself may be an emergent phenomenon, something that arises from deeper, timeless quantum processes. There is also the mystery of time's arrow, the fact that time seems to have a direction. We remember the past, but not the future. Eggs break, but do not spontaneously reassemble. Heat flows from hot to cold, but not the reverse. This directionality is encoded in the second law of thermodynamics, which states that entropy, or disorder, always increases in a closed system. But the fundamental laws of physics, at their deepest level, are time-symmetric. They work equally well whether time runs forward or backward. So where does the arrow of time come from? One answer is that it comes from the initial conditions of the universe. The Big Bang produced a universe in a state of extremely low entropy, highly ordered and uniform. Ever since then, the universe has been evolving toward higher entropy states, more disorder, more randomness. This increase in entropy gives time its arrow, its direction from past to future. But this explanation raises another question. Why did the universe begin in such a low entropy state? What determined those initial conditions? These questions bring us to the edge of what current physics can address. They point toward the need for a deeper theory, one that can describe not just how the universe evolves, but why it has the particular initial conditions it does, and perhaps even whether those initial conditions require any further explanation at all. As we sit with these ideas, let yourself feel the strangeness of time. This familiar thing that structures our every experience is, at its deepest level, far more mysterious than it appears. Time is not simply there, an unchanging backdrop. It is malleable, relative, possibly emergent, intimately connected with space and matter and energy. And at the origin of the universe, time itself may dissolve into something we do not yet have the concepts or the mathematics to fully describe. Breathe slowly and consider this. Every moment you experience, every memory you hold, every anticipation of the future is part of this strange, wonderful structure we call time. And that structure itself is part of the universe, woven into its fabric, inseparable from its existence. To ask about before the Big Bang is to ask about the origin of time itself, and that question takes us to the deepest mysteries of physics. Now that we have contemplated the nature of time, we can turn our attention to the Big Bang itself. What does this theory actually say? What do we know about those earliest moments of cosmic history? And perhaps more importantly, what does the Big Bang Theory not claim to explain? The Big Bang Theory is our best scientific account of the universe's history. It tells us that the universe began approximately 13.8 billion years ago in an extremely hot, dense state and has been expanding and cooling ever since. This is a statement about cosmic evolution, not cosmic origin. The theory describes how the universe has changed over time, but it does not claim to explain the ultimate origin of everything or why the Big Bang happened in the first place. Let us imagine ourselves moving backward in time, watching the universe run in reverse like a film played backward. Today, we see a vast cosmos filled with galaxies, each containing billions or trillions of stars, separated by enormous gulfs of space. As we move backward in time, we see these galaxies drawing closer together. The universe is smaller, denser, hotter. Continue backward, and the galaxies merge. The stars dissolve into plasma. The atoms themselves break apart into subatomic particles. Keep going, back through billions of years. The universe becomes so hot and dense that even atomic nuclei cannot hold together. We are now in the realm of quarks and gluons, the fundamental particles that make up protons and neutrons, all existing in a seething soup of unimaginable temperature and density. The entire observable universe, all the matter and energy that would eventually form billions of galaxies, is compressed into a region smaller than a single atom. This is the realm of the early Big Bang, the first tiny fractions of a second after the beginning. At these extreme conditions, our usual understanding of physics begins to break down. We approach what physicists call the Planck time, about 10 to the power of negative 44 seconds after the Big Bang. This is the smallest meaningful interval of time in physics, the point at which quantum effects of gravity become important and our current theories can no longer be trusted. The Big Bang Theory does not tell us what happened at the Planck time or before. It cannot, because we do not yet have a complete theory of quantum gravity that would allow us to describe such extreme conditions. The theory begins, in a sense, just after the Planck time and describes how the universe evolved from there. What happened in those first moments? In the first microsecond, the universe was filled with a roiling plasma of quarks, gluons, and other fundamental particles at temperatures exceeding 1 trillion degrees. As the universe expanded and cooled, these quarks combined to form protons and neutrons. After about 3 minutes, the universe had cooled enough for these protons and neutrons to combine into the simplest atomic nuclei, mostly hydrogen and helium, in a process called Big Bang nucleosynthesis. But the universe was still far too hot for atoms to form. Any electron that tried to attach to a nucleus would be immediately knocked away by the intense radiation filling the universe. For about 380,000 years, the universe remained in this state, opaque to light, a glowing fog of plasma. Then, as expansion continued and temperatures dropped, something remarkable happened. Electrons were able to combine with nuclei to form the first atoms. The universe became transparent to light. This transition, called recombination, is of immense importance to cosmology. The light that was streaming through the universe at that moment has been traveling ever since, stretched by cosmic expansion into microwave radiation. At these extreme conditions, our usual understanding of physics begins to break down. We approach what physicists call the Planck time, about 10 to the power of negative 44 seconds after the Big Bang. This is the smallest meaningful interval of time in physics, the point at which quantum effects of gravity become important and our current theories can no longer be trusted. The Big Bang Theory does not tell us what happened at the Planck time or before. It cannot, because we do not yet have a complete theory of quantum gravity that would allow us to describe such extreme conditions. The theory begins, in a sense, just after the Planck time and describes how the universe evolved from there. What happened in those first moments? In the first microsecond, the universe was filled with a roiling plasma of quarks, gluons, and other fundamental particles at temperatures exceeding 1 trillion degrees. As the universe expanded and cooled, these quarks combined to form protons and neutrons. After about 3 minutes, the universe had cooled enough for these protons and neutrons to combine into the simplest atomic nuclei, mostly hydrogen and helium, in a process called Big Bang nucleosynthesis. But the universe was still far too hot for atoms to form. Any electron that tried to attach to a nucleus would be immediately knocked away by the intense radiation filling the universe. For about 380,000 years, the universe remained in this state, opaque to light, a glowing fog of plasma. Then, as expansion continued and temperatures dropped, something remarkable happened. Electrons were able to combine with nuclei to form the first atoms. The universe became transparent to light. This transition, called recombination, is of immense importance to cosmology. The light that was streaming through the universe at that moment has been traveling ever since, stretched by cosmic expansion into microwave radiation. In far less than a second, the universe grew from something smaller than a subatomic particle to something many light years across. This might sound like science fiction, but inflation solves several puzzles that plague the standard Big Bang theory. It explains why the universe is so uniform on large scales, why the cosmic microwave background has almost exactly the same temperature in all directions. Before inflation, these regions were close enough together to reach thermal equilibrium. Inflation then stretched them apart so rapidly that they could no longer communicate, but they retained their uniform temperature from when they were in contact. Inflation also explains the origin of the tiny fluctuations we see in the cosmic microwave background. According to quantum mechanics, even empty space is not truly empty, but filled with quantum fluctuations, tiny random variations in energy. During inflation, these microscopic quantum fluctuations were stretched to cosmic scales, becoming the seeds of galaxies and large-scale structure. The patterns we see in the distribution of galaxies across the cosmos began as quantum fluctuations in the first inconceivably brief instant after the Big Bang. This is a profound idea. The vast structures of the universe, superclusters of galaxies stretching across hundreds of millions of light years, originated in quantum uncertainty at the smallest scales imaginable. The classical and the quantum, the large and the small, are intimately connected in the story of cosmic origins. Yet even inflation does not take us all the way back to the beginning. Inflation describes what happened during a particular phase of the universe's evolution, but it does not explain what caused inflation to begin or what the universe was like before inflation started. These remain open questions. The Big Bang theory, including inflation, is remarkably successful. The Big Bang theory, including inflation, is remarkably successful at explaining what we observe in the universe today. It accounts for the expansion of space, the cosmic microwave background, the abundance of light elements formed in the first minutes, the large-scale structure of galaxies, and countless other observations. It has made predictions that have been confirmed again and again. But it is important to understand what the theory does not claim. It does not say that the Big Bang was an explosion in space. Rather, it was an expansion of space itself, carrying matter and energy along with it. There is no center to this expansion, no edge. Every point in space is expanding away from every other point. If the universe is infinite in extent, it was already infinite at the Big Bang and has remained infinite, just with the distances between objects growing over time. The Big Bang theory also does not explain why the Big Bang happened, what caused it, or whether anything existed before it. These questions lie beyond the scope of the theory as it is usually formulated. To address them, we need to venture into more speculative territory, exploring ideas at the frontier of theoretical physics. As you rest in the contemplation of these ideas, consider the extraordinary journey of the universe from that hot, dense beginning to the rich, complex cosmos we inhabit today. From a state of near-perfect uniformity, with tiny quantum seeds of structure, has emerged the magnificent diversity of the universe: stars and planets, galaxies and clusters, nebulae and black holes. And somewhere in all that vastness, living beings capable of wondering about their origins. The Big Bang Theory is a triumph of human intellect and imagination, a framework for understanding cosmic history built from observation, mathematics, and reason. But it is also incomplete, leaving us with profound questions about the ultimate beginning. And it is to those questions, to the realm before or beyond the Big Bang, that we now turn our attention. To venture into the territory before the Big Bang, we must familiarize ourselves with quantum mechanics, the theory that governs the behavior of nature at its smallest scales. The realm of the quantum is strange and counterintuitive, operating according to rules that seem to defy common sense. Yet these rules are essential for understanding proposals about cosmic origins, because at the moment of the Big Bang, the entire universe was compressed to quantum scales. Imagine yourself shrinking down, becoming smaller and smaller, descending through the realm of everyday objects into the microscopic world of cells, then into the atomic realm, then smaller still into the subatomic. Here, in this domain of elementary particles and quantum fields, the familiar rules of classical physics no longer apply. Reality becomes probabilistic rather than deterministic, fuzzy rather than sharp, deeply interconnected in ways that seem to transcend space and time. The first principle of quantum mechanics to understand is superposition. In the classical world, an object has definite properties at all times. A coin is either heads or tails. A light is either on or off. A particle is either here or there. But in the quantum world, systems can exist in superpositions, being in multiple states simultaneously until they are measured or observed. An electron can be in a superposition of different positions, not just unknown to us, but genuinely in many places at once. A quantum system can be in a superposition of different energies, different orientations, different configurations. This is not merely a statement about our knowledge or ignorance. It is a statement about reality itself. Before measurement, the electron does not have a definite position that we simply have not discovered. It exists in a cloud of probability, simultaneously present in many locations. Only when we perform a measurement does the electron's wave function collapse, randomly selecting one of the possible positions to become actual. The second key principle is the uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that certain pairs of properties cannot both be measured precisely at the same time. The most famous example involves position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our measuring instruments. It is a fundamental feature of nature itself. The uncertainty principle has profound implications. It means that at the quantum level, there is an irreducible fuzziness to reality. You cannot pin down all properties of a system simultaneously. There is always some uncertainty, some indeterminacy. And crucially, this uncertainty extends to energy and time. For very brief periods, energy can fluctuate wildly without violating the conservation of energy. The shorter the time interval, the larger the allowed energy fluctuation. This leads to one of the most remarkable features of quantum mechanics. The quantum vacuum is not empty. Even in the absence of any particles or fields, in what we might think of as perfect emptiness, the quantum vacuum seethes with activity. Virtual particles constantly pop into and out of existence, borrowing energy from the vacuum for brief instants before annihilating and returning the energy. These vacuum fluctuations are not merely theoretical abstractions. They have measurable effects, such as the Casimir effect, where two uncharged metal plates in vacuum experience a tiny attractive force due to the quantum fluctuations between them. Think about what this means. At the deepest level, empty space is not truly empty, but filled with a dynamic foam of quantum activity. Particles and antiparticles flash into existence, exist for the briefest instant allowed by the uncertainty principle, and disappear. The vacuum is alive with possibility, with potential, with ephemeral structures that dance at the edge of existence. Another profound aspect of quantum mechanics is entanglement. When two quantum systems interact, they can become entangled, their properties correlated in ways that persist even when the systems are separated by vast distances. Measuring the state of one entangled particle instantaneously affects the state of its partner, no matter how far apart they are. Einstein famously called this spooky action at a distance and was deeply troubled by it. Yet experiments have confirmed that entanglement is real, a fundamental feature of quantum reality. Entanglement suggests that quantum systems cannot always be understood as independent entities. They are interconnected, part of a web of correlations that transcends space. In a sense, entangled particles share a single quantum state, even when separated by light years. This interconnectedness may have important implications for understanding the early universe, when everything was in close contact and potentially entangled in complex ways. Quantum mechanics also features wave-particle duality, the idea that quantum objects exhibit both wave-particle duality, the idea that quantum objects exhibit both wave-like and particle-like properties depending on how they are observed. Light, for instance, can behave as a wave, producing interference patterns, or as a stream of particles called photons. Electrons, traditionally thought of as particles, can produce interference patterns just like waves. This duality is not a contradiction, but a reflection of the fact that quantum objects are neither purely waves nor purely particles in the classical sense. They are quantum entities that transcend these categories. One of the most profound conceptual challenges posed by quantum mechanics concerns the role of measurement and observation. In the standard interpretation, the act of measurement causes the wave function to collapse, transforming a superposition of possibilities into a single actuality. But what counts as a measurement? Does it require a conscious observer? Does the wave function ever truly collapse? Or do all possibilities continue to exist in parallel universes, as the many worlds interpretation suggests? These questions remain deeply controversial among physicists and philosophers. For our exploration of cosmic origins, the key point is that quantum mechanics is essential for understanding the very early universe. At the Big Bang, all the matter and energy in the observable universe was compressed into a region far smaller than an atom, a domain where quantum effects dominate. The classical physics of Newton, or even Einstein's general relativity, cannot adequately describe such extreme conditions. We need quantum mechanics. But there is a problem. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and fields at small scales. These two theories are our most successful frameworks for understanding nature, yet they are fundamentally incompatible. General relativity assumes space-time is smooth and continuous. Quantum mechanics suggests everything, including space-time itself, should be subject to quantum fluctuations and uncertainty. At normal scales, this incompatibility does not matter. Gravity is so weak compared to other forces that quantum effects of gravity are negligible. But at the Planck scale, about 10 to the power of -35 meters, and 10 to the power of negative 44 seconds. Both gravitational and quantum effects become equally important. At this scale, space-time itself becomes turbulent, subject to violent quantum fluctuations. This is the realm of quantum gravity, and we do not yet have a complete, verified theory to describe it. Without a theory of quantum gravity, we cannot definitively say what happened at the very instant of the Big Bang or what might have existed before. This is not a temporary gap in knowledge that will soon be filled. It is a fundamental limitation of our current understanding. The Planck scale represents a barrier beyond which our best theories cannot reliably take us. And yet, theoretical physicists have developed various approaches to quantum gravity, different frameworks for reconciling general relativity and quantum mechanics. These include string theory, loop quantum gravity, causal set theory, and others. Each offers different insights into what space-time might be like at the Planck scale and what the quantum nature of the universe's origin might involve. As you breathe slowly and let these ideas settle in your mind, appreciate the strangeness and beauty of the quantum realm. This is the foundation of all matter and energy, a world where possibilities exist in superposition, where empty space teems with activity, where distant objects share a mysterious connection, where the act of observation shapes reality itself. And this quantum realm may hold the key to understanding the deepest mystery of all, the origin of the universe and what, if anything, came before the Big Bang. The quantum world invites us to release our attachment to certainty and determinism, to embrace probability and potentiality. It asks us to accept that at the deepest level, reality is not a machine clicking along according to predetermined rules, but a tapestry of possibilities, collapsing into actuality through processes we still do not fully understand. And in that acceptance, there is a kind of peace, a recognition that mystery is not a defect in our knowledge, but a feature of the universe itself. Among the various approaches to understanding cosmic origins, one of the most elegant and thought-provoking is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the early 1980s. This proposal offers a way to think about the beginning of the universe that dissolves the question of what came before the Big Bang by suggesting that before may not be a meaningful concept in the context of quantum cosmology. Imagine asking what lies south of the South Pole. The question seems grammatically correct, but it has no answer because the South Pole is the southernmost point on Earth. There is no further south to go. The Hartle-Hawking proposal suggests that asking what happened before the Big Bang is a similar question, not because we lack information, but because the structure of space-time itself makes before meaningless. The key insight of the no-boundary proposal involves a concept called imaginary time. In physics, we are accustomed to thinking of time as a real number, ticking forward from one moment to the next. But in quantum mechanics, time can also be treated as an imaginary number, multiplied by the square root of -1. This is not mere mathematical trickery. Using imaginary time can simplify quantum calculations and reveal deep symmetries in physical laws. Hawking proposed that in the very early universe, at the quantum scale, time might have had an imaginary component. Instead of being purely time-like, it was partly space-like. In this regime, the distinction between time and space blurs. All four dimensions of space-time become similar in character, all space-like. This is sometimes described as Euclidean spacetime, after the familiar Euclidean geometry where all dimensions have the same status. Now, here is where the proposal becomes profound. In Euclidean spacetime, where time is imaginary, the universe can be described as finite but without boundary. To understand this, imagine the surface of a sphere. It is finite in extent, having a definite area, but it has no edge, no boundary. You can travel anywhere on the sphere's surface without ever encountering a place where the surface ends. The sphere is complete and self-contained. Hartle and Hawking proposed that the universe in its quantum origin might be like this. If we go back to the very beginning and use imaginary time, the universe resembles a sphere in 4 dimensions. Just as a sphere has no boundary in space, the universe has no boundary in space-time. There is no edge, no beginning point, no first moment. The universe is simply complete in itself. But what does this mean for our ordinary experience of time? Hartle and Hawking suggested that as the universe expanded and evolved, time transitioned from being imaginary to being real, from being space-like to being time-like. In the very early quantum regime, there was no distinction between time and space. As the universe grew larger and classical physics became applicable, time emerged as the distinct dimension we experience, with its arrow pointing from past to future. In this picture, asking what happened before the Big Bang is like asking what lies south of the South Pole. Near the beginning, in the regime where imaginary time applies, there is no direction that corresponds to earlier. Time curves back on itself in a way that eliminates the need for an initial boundary condition or a first moment. The universe is self-contained, requiring no external cause or creator to set it in motion. This proposal has profound philosophical implications. It suggests that the universe can be entirely self-explanatory, at least in terms of its physical laws. There is no moment of creation, no first cause to explain. The universe simply is, complete and finite in imaginary time, infinite in real time. As Hawking himself noted, this approach leaves no room for a creator to act, no gap in which divine intervention is needed to start the cosmic machinery. Of course, the no-boundary proposal does not explain why the universe has the particular laws of physics it does, or why quantum mechanics and general relativity operate as they do. These are deeper questions that may require different kinds of answers, or they may be questions that have no answers at all, merely brute facts about reality. The mathematical formulation of the no-boundary proposal is complex, involving path integrals over all possible space-time geometries. The idea is that the quantum state of the universe is determined by summing over all possible histories, all possible ways that space-time could have configured itself, weighted by their quantum probabilities. Among all these possibilities, certain configurations are more probable, and these correspond to the smooth, slowly expanding universe we observe emerging from the Big Bang. One remarkable feature of this approach is that it makes predictions about the initial conditions of the universe. It suggests that the universe should have started in a state of maximum symmetry and smoothness, exactly what we observe in the cosmic microwave background. The tiny fluctuations we see, the seeds of galaxies, arise naturally from quantum effects in this framework. However, the no-boundary proposal is not without its challenges and critics. Some physicists have raised questions about the mathematical consistency of the approach, about whether the path integral over geometries is well-defined, and whether it truly predicts a universe like ours. There are also questions about the interpretation of imaginary time. Is it merely a mathematical device for simplifying calculations, or does it represent something physically real about the early universe? Stephen Hawking himself continued to refine and defend the no-boundary proposal throughout his career, sometimes in collaboration with other physicists like Thomas Hertog. In his later work, Hawking explored connections between the no-boundary proposal and holographic principles, ideas suggesting that the information content of a region of space can be encoded on its boundary, like a hologram. These explorations led to new insights about the quantum nature of space-time and the deep structure of physical law. Whether or not the no-boundary proposal is ultimately correct, it represents a beautiful example of how quantum mechanics and general relativity can be brought together to address the question of cosmic origins. It shows how the mathematics of theoretical physics can lead us to ideas that are both profoundly strange and intellectually satisfying, dissolving apparent paradoxes and opening new ways of thinking about the universe. As you contemplate the no-boundary proposal, let yourself appreciate its elegance. The idea that the universe is self-contained, finite yet boundless, needing no external cause or initial condition, has a certain aesthetic appeal. It suggests a cosmos that is complete in itself, whose existence requires no further explanation beyond the laws of physics that describe it. And yet, even if this proposal is correct, it leaves us with the question of why these particular laws apply, why there is something rather than nothing. These may be questions that physics alone cannot answer, questions that touch on metaphysics and philosophy as much as science. But that is part of the beauty of this exploration. We are not merely seeking technical answers, but engaging with the deepest mysteries of existence. Breathe gently and feel the strangeness of a universe with no boundary, no beginning, no first moment in imaginary time, yet experienced by us as having a definite history, a clear arrow of time pointing from the Big Bang to the present and onward into the future. This duality, this interplay between the timeless quantum realm and our temporal experience, is one of the most profound puzzles in all of physics. While the Hartle-Hawking proposal addresses the question of what came before the Big Bang by suggesting the question itself may be meaningless, there is another approach that takes a very different tack. This is the idea of eternal inflation, which proposes that the Big Bang was not the beginning of everything, but merely one event among countless others in an eternally inflating cosmos, a vast multiverse where universes bubble into existence continuously. To understand eternal inflation, we must return to the concept of inflation itself, the brief period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. Inflation was originally proposed to solve certain problems in standard Big Bang cosmology, such as why the universe is so uniform on large scales and why it has the particular geometry it does, nearly flat rather than curved. The inflationary mechanism relies on a hypothetical field called the inflaton field, which permeates space. This field has an associated energy, and when the field is in a particular high-energy state, it causes space to expand exponentially fast. As inflation proceeds, the inflaton field eventually rolls down to a lower energy state. Inflation ends, and the energy stored in the field converts into particles and radiation, producing the hot, dense conditions of the standard Big Bang. This is the picture of simple inflation, a single episode of rapid expansion followed by normal cosmic evolution. But in the 1980s, physicists including Alan Guth, Andre Linde, and others realized that if inflation can happen once, it might happen over and over again, eternally. The key insight is that inflation is a quantum process, subject to quantum fluctuations. Imagine a region of space where the inflaton field is in its high-energy state, causing rapid expansion. Due to quantum fluctuations, different parts of this region experience slightly different histories. In some regions, the inflaton field quickly rolls down to its low-energy state and inflation ends. In other regions, quantum fluctuations push the field back up to higher energy, causing those regions to continue inflating. Now here is the crucial point. The regions that continue inflating expand so rapidly that they quickly dominate the total volume of space. Even though in most regions inflation eventually ends, there are always some regions where it continues, and these inflating regions grow exponentially. The result is that inflation never entirely stops. It ends in some regions, producing pocket universes like ours, but continues in others, which in turn spawn more pocket universes, and so on forever. This is eternal inflation, a self-perpetuating process that, once started, can never completely end. The cosmos becomes a vast, infinite expanse in which bubble universes are constantly forming, each experiencing its own Big Bang as inflation ends in that region, while the surrounding space continues to inflate eternally. In this picture, our observable universe, everything we can see out to the farthest reaches of our telescopes, is just one bubble among an infinite number of bubbles. Each bubble universe has its own Big Bang, its own cosmic history, potentially its own laws of physics. We are like inhabitants of a single bubble, unable to see beyond our cosmic horizon to the rest of the eternally inflating multiverse. The implications are staggering. If eternal inflation is correct, then the Big Bang was not the beginning of everything. It was the beginning of our local region, our bubble universe. But the larger cosmos has always existed and will always continue to exist, birthing new universes without end. Moreover, the different bubble universes may have different physical properties. String theory and other approaches to fundamental physics suggest that the laws of physics we observe, such as the masses of particles and the strengths of forces, may not be unique. There may be a vast landscape of possible vacuum states, each corresponding to different effective laws of physics. As different bubbles nucleate in the eternally inflating space, they may settle into different vacuum states, acquiring different physical laws. This is the multiverse hypothesis, the idea that there are not only many universes but many kinds of universes, exploring different possibilities in the landscape of physical law. Some of these universes might be hospitable to life, with the right balance of forces and particles to allow stars and planets and chemistry. Others might be lifeless, with physical constants so different that nothing interesting can happen. In this framework, the question of why our universe has the particular properties it does has a striking answer. There are many universes with many different properties, and we find ourselves in one suitable for life simply because we could not exist in the others. This is an application of the anthropic principle, the idea that the properties we observe are partly selected by the requirement that the universe must be capable of supporting observers. Some physicists find the multiverse hypothesis deeply satisfying, a natural consequence of inflation combined with quantum mechanics and modern theories of fundamental physics. Others find it troubling or even unscientific, because the other universes in the multiverse may be forever beyond our observational reach, unable to be directly tested or confirmed. And yet, there are potential ways to test aspects of the multiverse idea. If our bubble universe underwent a collision with another bubble universe in the distant past, it might have left traces in the cosmic microwave background, subtle anomalies in the temperature patterns that could potentially be detected. Physicists have looked for such signatures, so far without finding convincing evidence, but the search continues. The idea of eternal inflation also raises fascinating questions about probability and prediction. In an infinite multiverse where everything that can happen does happen infinitely many times, how do we make sense of probabilities? How do we predict what we should observe? These questions have led to a branch of research called eternal inflation cosmology, grappling with the measure problem, the question of how to assign probabilities to events in an infinite, eternally inflating cosmos. Some versions of eternal inflation suggest that the multiverse may have no beginning in time, that it has always existed in a state of eternal inflation. Our universe would then be just one finite episode in an infinite, eternal process. Other versions suggest that eternal inflation itself had a beginning, perhaps from a state of quantum gravity, perhaps from a prior contracting phase, or perhaps from the kind of timeless quantum state proposed by Hartle and Hawking. As you sit with these ideas, feel the vastness they imply. If eternal inflation is correct, our universe, vast as it is with its billions of galaxies, is but an infinitesimal bubble in an infinite ocean of bubbles, each with its own history, possibly its own laws. The Big Bang was not the beginning of all existence, but merely the beginning of our local patch of existence. This perspective can be both humbling and liberating. Humbling because it suggests our universe is not unique or special in any cosmic sense, just one among infinitely many. Liberating because it opens up endless possibilities, a multiverse of infinite variety and wonder. Somewhere in this vast landscape, there may be universes where the laws of physics are barely different from ours, universes with their own galaxies and stars, perhaps their own forms of life. And there may be universes utterly alien, operating according to principles we cannot even imagine. Yet even in the face of this infinite abundance, we are here, conscious observers experiencing this particular universe with its particular properties. That is not diminished by the existence of countless other universes. If anything, it becomes more remarkable. We are part of this vast cosmic story, participants in the eternal drama of creation and existence. Breathe deeply and let yourself rest in the contemplation of infinity, of endless universes bubbling into being, of a cosmos so vast that our imaginations can barely begin to grasp it. This is the vision offered by eternal inflation, a universe without end, forever creating new realms of possibility. Among the most ambitious attempts to understand the fundamental nature of reality, and thereby to address the question of cosmic origins, is string theory. This theoretical framework proposes that the ultimate constituents of the universe are not point-like particles, but tiny vibrating strings of energy. The different vibrations of these strings correspond to different particles, like notes played on a cosmic instrument. String theory is complex and mathematically rich, and it has profound implications for thinking about what might have existed before the Big Bang. String theory emerged in the late 1960s and early 1970s, initially as an attempt to describe the strong nuclear force. It was later realized that one of the vibrational modes of strings corresponded exactly to the graviton, the hypothetical quantum particle that mediates gravity. This was a stunning discovery, suggesting that string theory might be a unified theory, a single framework capable of describing all forces and particles, including gravity. But string theory comes with a price. For the mathematics to be consistent, the strings must vibrate not in the familiar 3 dimensions of space plus 1 of time, but in 9 dimensions of space plus 1 of time, a total of 10 dimensions. Where are these extra dimensions? The standard answer is that they are curled up, compactified into tiny shapes, so small that we cannot detect them directly. At every point in the 3-dimensional space we experience, there are 6 additional dimensions, wrapped up into intricate geometric structures. The shape of the compactified dimensions determines the physics we observe in our 3-dimensional world. Different shapes lead to different effective laws of physics, different particles, different forces. This gives rise to the landscape problem in string theory. There may be a vast number of possible ways to compactify the extra dimensions, perhaps 10 to the power of 500 or even more, each corresponding to a different possible universe with different physical laws. This landscape connects to the multiverse ideas we encountered earlier. If different regions of space compactify in different ways, or if different bubble universes in an eternally inflating multiverse settle into different compactifications, then the multiverse could explore many or all of the possibilities in the string theory landscape. Our universe would be one particular solution, one particular way the extra dimensions happen to be curled up in our local region. But what does string theory tell us about the Big Bang and what came before? Here, the brain world scenarios become relevant. In string theory, strings are not the only objects. There are also extended objects called brains, short for membranes. These brains can have various dimensions. One-dimensional brains are strings, 2-dimensional brains are surfaces, three-dimensional brains are volumes, and so on. Our universe might itself be a three-dimensional brain floating in the higher dimensional space of string theory, called the bulk. Matter and forces, except for gravity, are confined to our brain. Gravity, being associated with the geometry of space-time itself, can propagate through the bulk. This could explain why gravity is so much weaker than the other forces, its strength diluted by spreading into extra dimensions. In the ekpyrotic scenario we discussed earlier, the Big Bang arises from a collision between brains. But there are other possibilities. Perhaps the Big Bang occurred when our brain butted off from another brain, or when it underwent some kind of topological transition in the higher dimensional space. The details depend on the specific string theory model and the geometry of the extra dimensions. One intriguing idea is the notion of a pregeometric phase. String theory suggests that at sufficiently high energies or small scales, the usual concepts of space and time break down. Space-time itself becomes fuzzy, subject to quantum fluctuations, and eventually dissolves into something more fundamental. This pregeometric regime might have characterized the universe before the Big Bang. In this pregeometric phase, there would be no space-time as we understand it, no meaningful notion of distance or duration. Instead, there would be a quantum foam of stringy fluctuations, a kind of primordial chaos from which space-time gradually crystallized as the universe expanded and cooled. The Big Bang would mark the transition from this pregeometric state to the classical space-time we experience. This idea connects to the broader notion in string theory that space-time is not fundamental but emergent. Just as temperature emerges from the collective motion of many atoms, space-time might emerge from some more fundamental quantum structures. Before the emergence of space-time, the question of what existed becomes almost impossible to formulate in our usual language, because that language presupposes the existence of time and space. String theory also offers insights into the nature of black holes, and these insights may be relevant to the Big Bang. Black holes, regions where gravity is so strong that nothing can escape, have deep connections to thermodynamics and quantum mechanics. Stephen Hawking showed that black holes emit radiation and have a temperature, suggesting they are thermodynamic systems with entropy. But what are the microstates, the detailed configurations, that give a black hole its entropy? String theory provides an answer, at least in certain cases. The microstates are configurations of strings and brains. This success lends credibility to string theory's claim to be a quantum theory of gravity. And the techniques developed for understanding black hole microstates might eventually be applied to understanding the early universe, which in many ways resembles the interior of a black hole, with extreme densities and quantum gravitational effects. Another fascinating aspect of string theory is holography, the idea that the information content of a volume of space can be encoded on its boundary. This principle emerged from the study of black holes and has led to deep insights about quantum gravity. The ADS/CFT correspondence, a concrete realization of holography, relates a theory of gravity in a higher dimensional anti-de Sitter space to a quantum field theory on its boundary. This correspondence has been used to study a wide range of problems, from quark-gluon plasmas to quantum entanglement. Holography suggests that our three-dimensional universe might be a holographic projection of information encoded on a two-dimensional cosmic boundary. If this is true, the question of what came before the Big Bang might have a reformulation in terms of the evolution of information on this boundary. The apparent beginning of the universe in time might correspond to some kind of transition or initial state in the boundary theory. As you rest in contemplation of these ideas, feel the strangeness of extra dimensions curled up at every point in space, invisible to our senses but essential to the underlying structure of reality. Imagine strings vibrating in 10 dimensions, their patterns generating all the particles and forces we observe. Consider a universe that is a three-dimensional brain floating through a higher-dimensional bulk, its birth perhaps triggered by a collision or transition in that vaster space. String theory is beautiful and mathematically rich, but it is also incomplete and unproven. We do not yet have direct experimental evidence for strings or extra dimensions. The theory makes few definite predictions that can be tested with current technology. Some physicists see string theory as the most promising path to a unified understanding of nature. Others view it as an elegant mathematical structure that may not describe our physical universe at all. Regardless of its ultimate truth, string theory expands our imagination of what is possible. It shows us that reality might be vastly richer and stranger than appearances suggest, that the three dimensions we navigate and the single dimension of time we experience might be just a fragment of a higher dimensional tapestry. And in this expanded conceptual space, new possibilities for understanding cosmic origins emerge, possibilities that may eventually lead us to an answer to the question of what, if anything, existed before the Big Bang. Breathe gently and allow these ideas to wash over you without demanding full comprehension. String theory operates in realms far beyond everyday intuition, in spaces with dimensions we cannot visualize, with structures we can describe mathematically but not picture. This is the frontier of human understanding, where physics becomes almost indistinguishable from pure mathematics, where the universe reveals itself to be more subtle and complex than we ever imagined. While string theory is perhaps the most well-known approach to unifying quantum mechanics and general relativity, it is not the only one. Other researchers have developed alternative frameworks for quantum gravity, each offering different insights into the nature of space-time at the Planck scale and different perspectives on the question of cosmic origins. One prominent alternative is loop quantum gravity, or LQG. Unlike string theory, which introduces new fundamental objects like strings and branes, loop quantum gravity takes Einstein's general relativity and applies the techniques of quantum mechanics to it directly. The result is a theory in which space-time itself is quantized, woven from discrete loops and networks at the smallest scales. In loop quantum gravity, space is not a smooth continuum but a quantum foam, a network of nodes connected by links. Each node represents a quantum of volume, each link a quantum of area. These quanta are incredibly small, on the order of the Planck length, about 10 to the power of -35 meters. At larger scales, this discrete network gives rise to the smooth space-time we experience, just as a fabric appears smooth from a distance but reveals its woven structure when examined closely. Time, in loop quantum gravity, is more subtle. There is no universal time ticking away independently of matter and energy. Instead, time emerges from the quantum dynamics of the gravitational field and matter, from the correlations between different parts of the system. This relational view of time has deep philosophical implications, suggesting that time is not an absolute backdrop, but a way of describing how things change relative to each other. When applied to cosmology, loop quantum gravity produces the loop quantum cosmology we mentioned earlier, in which the Big Bang singularity is replaced by a quantum bounce. As the universe contracts, the density and curvature increase but never become infinite. Quantum gravitational effects create a repulsive force that halts the collapse and reverses it into expansion. The Big Bang is the moment of maximum contraction and minimum volume, a quantum state rather than a classical singularity. This bounce might be unique, a single transition from a contracting pre-Big Bang universe to our current expanding universe. Or it might be part of an endless series of bounces, a cyclic cosmology driven by loop quantum gravity. Either way, the theory suggests there was something before the Big Bang, a contracting universe, governed by the same quantum gravitational laws that govern our current universe, but in a different phase of its evolution. Loop quantum gravity also addresses the problem of time in quantum cosmology. If the universe is all there is, if there is no external reference frame, then how do we define time? Wheeler and DeWitt, in their approach to quantum cosmology, derived an equation in which time disappears, the Wheeler-DeWitt equation. The wave function of the universe does not evolve in time. Instead, it is a timeless object, describing all possible configurations of the universe at once. This timelessness is puzzling. We experience time flowing, yet the deepest equations of quantum cosmology seem to eliminate it. Loop quantum gravity offers a resolution by showing how time can emerge from timeless quantum states through a process called deparameterization. Certain variables play the role of a clock, and evolution with respect to this internal clock gives rise to the time we experience. Another approach to quantum gravity is causal set theory. This theory proposes that at the most fundamental level, space-time is not continuous or even a quantum network, but a discrete set of events related by causal connections. Imagine space-time as a collection of points, where each point represents a fundamental event, and points are related if one can causally influence the other, if a signal could travel from one to the other. In causal set theory, the structure of space-time emerges from the pattern of these causal relationships. The theory is based on the idea that causality, the notion that events can influence other events in a particular order, is more fundamental than space or time individually. Space-time, with its geometry and dimensionality, is a large-scale approximation that emerges from the underlying causal structure. Applied to cosmology, causal set theory suggests that the universe might have had a finite beginning in terms of the number of fundamental events, but this beginning need not correspond to a singularity or infinite density. The discrete nature of the causal set prevents infinities from arising. The theory also allows for the possibility of a universe that fluctuates into existence from nothing, as a quantum event in the causal set structure. Yet another approach is asymptotic safety, a program that seeks to make general relativity itself a complete quantum theory by showing that it is well-defined at all energy scales. The idea is that at very high energies, near the Planck scale, the strength of gravity becomes weaker rather than stronger, approaching a fixed point where the theory becomes simple and predictable again. If this is true, quantum gravity might not require strings or loops or any new fundamental structures. Einstein's equations themselves, appropriately understood, might suffice. Asymptotic safety is still being developed and tested, but if it proves correct, it would offer a conservative path to quantum gravity, one that does not revolutionize our picture of space-time, but instead shows that the classical picture can be extended into the quantum regime. For cosmology, this might mean that the universe can be described by Einstein's equations even at the Big Bang, with quantum corrections that prevent singularities and allow for a bounce or a smooth beginning. There are also approaches based on emergent gravity, the idea that gravity is not a fundamental force, but an emergent phenomenon arising from more fundamental quantum processes. The most famous proponent of this idea was Eric Verland, who proposed that gravity emerges from the tendency of quantum systems to maximize entropy. If gravity is emergent, then the question of quantum gravity becomes a question of understanding the fundamental quantum system from which gravity emerges. Emergent gravity perspectives suggest that space-time itself might be emergent, a macroscopic description that does not apply at the most fundamental level. Before the Big Bang, in the regime where space-time has not yet emerged, the universe would be described by whatever fundamental quantum system underlies space-time. This might be a quantum field theory, a quantum information structure, or something we have not yet imagined. All of these approaches to quantum gravity are works in progress. None has been definitively confirmed or refuted by experiment. This is one of the great frustrations of quantum gravity research. The energies needed to directly test these theories are far beyond what we can produce in laboratories. The Planck energy is about 10 to the power of 19 gigaelectronvolts, while the Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies around 10 to the power of 4 gigaelectronvolts. We are many orders of magnitude away from directly probing the Planck scale. Yet indirect tests are possible. Cosmology itself is a laboratory for quantum gravity. The very early universe was a quantum gravitational system, and it may have left imprints in the cosmic microwave background or in the distribution of large-scale structure. Physicists search for these signatures, hoping to find evidence that will point toward the correct theory of quantum gravity. As you breathe slowly and settle into these ideas, appreciate the diversity of approaches to understanding the quantum nature of space-time. Researchers are exploring many paths, using different mathematical tools, making different assumptions about what is fundamental. This is how science progresses at the frontier, through the creative exploration of many possibilities, some of which will prove fruitful and others dead ends, but all of which expand our understanding. The quest for quantum gravity is ultimately the quest to understand space-time itself at its deepest level. And with that understanding comes the possibility of answering what existed before the Big Bang, or whether that question has meaning. Perhaps space-time is quantized loops. Perhaps it is an emergent hologram. Perhaps it is a causal set or a smooth continuum made safe at high energies. We do not yet know, but the search itself is beautiful, a testament to human curiosity and our drive to understand the cosmos. Rest now in the contemplation of these quantum geometries, these discrete networks and causal structures, these emergent spacetimes and bouncing cosmologies. Each approach offers a window into a possible deep reality, a glimpse of how nature might operate at scales far beyond our direct perception. And in this plurality of approaches, we see not confusion but richness, not failure but the honest acknowledgement that we are still learning, still discovering, still reaching toward a complete understanding of the quantum cosmos. As we have journeyed through various theories and models addressing what might have existed before the Big Bang, we have encountered a recurring theme: the limitations of what we can know. These limitations are not merely practical, a matter of building better telescopes or more powerful accelerators. They are fundamental, woven into the fabric of physics and epistemology, the nature of knowledge itself. One of the deepest limitations concerns the cosmic horizon. Because the speed of light is finite and the universe has a finite age, there is a maximum distance we can observe. Light from more distant regions has not had time to reach us. This defines the observable universe, a sphere centered on us with a radius of about 46 billion light-years, taking into account the expansion of space. Beyond this horizon, there may be more universe, perhaps infinitely more, but it is forever beyond our direct observation. This means that many of the ideas we have discussed, such as eternal inflation creating an infinite multiverse, may be inherently untestable. If other bubble universes exist beyond our cosmic horizon, we cannot see them, visit them, or communicate with them. They are, from our perspective, as inaccessible as parallel dimensions, or past universes in a cyclic model that has long since contracted and bounced into our current expansion. Some philosophers and physicists argue that untestable theories are not scientific, that science requires empirical verification, the ability to test predictions against observations. If we cannot observe other universes, if we cannot probe the Planck scale structure of space-time, if we cannot see beyond our cosmic horizon, then theories about these domains are mere speculation, perhaps interesting philosophy or mathematics, but not physics. Others respond that science has always dealt with unobservable entities and that indirect evidence can suffice. We cannot directly observe quarks or black hole interiors, yet we consider theories about them scientific because they make predictions about things we can observe. Similarly, theories about the multiverse or quantum gravity might make predictions about the cosmic microwave background, the distribution of galaxies, or other observable phenomena, even if they also posit unobservable realms. This debate touches on the philosophy of science itself. What makes a theory scientific? Is it falsifiability, the ability to be proven wrong by observation? Is it explanatory power, the ability to account for diverse phenomena with simple principles? Is it mathematical consistency and beauty? Different philosophers and scientists emphasize different criteria, and there is no universal agreement. Another fundamental limitation arises from quantum mechanics itself. The Heisenberg uncertainty principle tells us that certain properties cannot be measured precisely at the same time. This is not just a limitation of our instruments, but a statement about reality. At the quantum level, the universe is fundamentally indeterminate, fuzzy, probabilistic. We cannot predict the exact outcome of quantum measurements, only the probabilities of different outcomes. Applied to cosmology, this suggests that even if we had perfect theories and perfect observations, we could not determine the exact initial state of the universe. Quantum fluctuations ensure there is always some irreducible uncertainty. The best we can do is describe the wave function of the universe, the superposition of all possible states, weighted by their probabilities. But which particular state was realized, which set of quantum fluctuations became actual, involves an element of pure chance. This probabilistic nature of quantum mechanics raises profound questions when applied to the universe as a whole. In standard quantum mechanics, we talk about measurements made by observers. But if the universe is everything, who is the observer? What causes the wave function of the universe to collapse, selecting one outcome from many possibilities? Or does it never collapse, with all possibilities remaining real in some sense? As in the many worlds interpretation? These questions do not have settled answers. They are part of the ongoing debate about the interpretation of quantum mechanics, a debate that has continued for nearly a century without resolution. Different interpretations, such as the Copenhagen interpretation, many worlds, pilot wave theory, and others, offer different views on the nature of reality and the role of observation. And these different views lead to different perspectives on cosmic origins. There is also the problem of initial conditions. Even if we have a complete theory of quantum gravity, even if we understand what happened at the Planck time and before, we must still specify the initial state of the universe. Why did the universe begin in one particular state rather than another? Can physics explain the initial conditions, or are they simply brute facts that we must accept? Some theories, like the Hartle-Hawking no-boundary proposal, attempt to eliminate the need for initial conditions by making the universe self-contained, with no initial boundary. Others, like eternal inflation, make the specific initial conditions of our universe less significant by embedding it in a vast multiverse where all possible initial conditions are realized somewhere. Still others propose that the initial conditions themselves evolved from a prior state, pushing the question back, but not eliminating it. Ultimately, we may be asking questions that have no answers within physics. Why is there something rather than nothing? Why do these particular laws of physics govern the universe? Why does the universe exist at all? These are metaphysical questions, questions about the nature of being and existence. Physics can tell us how the universe behaves, how it evolves, perhaps even how it began in a physical sense. But it may not be able to tell us why there are laws of physics at all, why they have the form they do, or why existence is preferred to non-existence. Some physicists and philosophers embrace this limitation, accepting that there are questions beyond the scope of science. Others continue to hope for a final theory, a theory of everything that would explain not just all physical phenomena, but also why the universe must exist and must have the particular laws it does. This hope motivates much work in theoretical physics, the search for mathematical necessity, for a unique set of laws that could not be otherwise. Roger Penrose, for instance, has suggested that the laws of physics have a kind of mathematical inevitability, that they reflect deep truths about the structure of logic and mathematics. In this view, the universe is not arbitrary, but follows from mathematical necessity. Discovering the final laws of physics would be discovering these necessary mathematical truths. But even if this is correct, it shifts the mystery from why these laws to why does mathematics determine reality, or why is there a logical necessity that manifests as physical law? Another perspective comes from the anthropic principle, which we touched on earlier. The weak anthropic principle simply notes that we observe a universe compatible with our existence because we could not exist otherwise. The strong anthropic principle suggests that the universe must have properties allowing life and consciousness because its purpose or nature requires observers. And the final anthropic principle, more speculative still, suggests that once life and intelligence arise in the universe, they will persist and eventually shape the cosmos itself. Anthropic reasoning is controversial. Critics argue it is a cop-out, an abandonment of the search for deeper explanations. Proponents argue it is a legitimate way to understand why the universe has the particular properties it does, especially if combined with multiverse theories. If there are many universes with varying properties, the fact that we find ourselves in one suitable for life is unsurprising and requires no further explanation. As you sit quietly with these philosophical questions, allow yourself to appreciate the limits of knowledge. Science is powerful, but it is not omniscient. There are boundaries to what we can observe, limits to what we can predict, questions we may never answer. This is not a failing of science, but a recognition of its scope and proper domain. Science tells us about the physical world, about matter and energy, space and time, cause and effect within the natural realm. But questions about ultimate purpose, about why there is something rather than nothing, may lie beyond its reach. And yet, even in acknowledging these limits, there is a kind of peace. We do not need to have all the answers. The mystery of existence is part of its beauty. The fact that we can ask these questions, that we can contemplate the nature of reality and our place in it, is itself remarkable. We are the universe becoming conscious of itself, matter and energy arranged in such a way as to ponder its own origins. Breathe deeply and rest in this awareness. You are part of the cosmic story, a chapter in the great unfolding of existence. The questions we have explored together about what came before the Big Bang, about the nature of time and space, about the origin and structure of reality, these are among the deepest questions humans have ever asked. We may never have complete answers, but the asking itself is a form of participation in the mystery, a way of engaging with the profound gift of existence. Throughout our exploration, we have grappled with the concept of time, with the idea of before and after, past and future. We have seen that time is far stranger than it appears in everyday experience, that it may not be fundamental but emergent, that at the origin of the universe it may not exist at all in the usual sense. Now, let us go deeper into these ideas, exploring perspectives that challenge our most basic assumptions about the nature of time. One such perspective is the block universe view, also called eternalism. According to this view, which finds support in Einstein's theory of relativity, time does not flow. The past, present, and future all exist equally and simultaneously. The entire history of the universe, from the Big Bang to its ultimate fate, is laid out in a four-dimensional space-time block. We experience only one three-dimensional slice at a time, which we call the present. But this is a feature of our consciousness, not a feature of the universe itself. In the block universe, asking what came before the Big Bang is like asking what lies to the left on a map. It depends on your orientation, your perspective. The Big Bang is simply one end of the space-time block. There is no time before it, not because time began, but because before refers to a direction in time, and the Big Bang is the boundary in that direction. Just as a sphere has no point beyond its surface, the space-time block has no events before the Big Bang. This view can be disconcerting. It seems to eliminate free will, to make change an illusion, to render the present moment no more special than any other. And yet, it aligns well with the mathematics of relativity. In relativity, there is no universal now, no objective present moment. Different observers in relative motion will disagree about which events are simultaneous, about which events are in the past, and which in the future. This relativity of simultaneity suggests that the present is not an objective feature of the universe, but a subjective experience. If the block universe view is correct, then in a very real sense, the Big Bang still exists, as does every moment that will ever occur. You exist not just now, but at every moment of your life simultaneously, each moment eternal in its place in the space-time block. The flow of time, the sense of passing from one moment to the next, is an illusion, or at least a phenomenon of consciousness rather than of the external world. But there are other perspectives that take the reality of time more seriously. The growing block universe view suggests that the past and present exist, but the future does not yet exist. The universe is a block that is constantly growing, with new moments being added as time flows forward. In this view, time's passage is real, not an illusion, and the present moment is genuinely special as the boundary between the fixed past and the open future. Yet another view is presentism, the idea that only the present moment exists. The past no longer exists, having been replaced by the present. The future does not yet exist. Reality is confined to the now, to the current state of the universe. This view aligns well with our intuitive experience, but conflicts with relativity, which undermines the notion of a universal present. These different views of time have implications for understanding the Big Bang. In the block universe view, the Big Bang is simply one end of the eternal space-time structure. In the growing block view, the Big Bang is the first moment, the beginning of the growth process. In presentism, the Big Bang is long past, no longer existent, known to us only through its effects on the present. But there is a more radical possibility, one suggested by quantum cosmology and certain interpretations of quantum mechanics. This is the idea that time is not fundamental at all, but emerges from something deeper, something timeless. We touched on this earlier with the Wheeler-DeWitt equation, where the wave function of the universe does not evolve in time, but simply is a timeless mathematical object describing all possible configurations of the universe. In this timeless view, the universe in its deepest description has no temporal aspect. It is a quantum superposition of all possible space-time geometries and matter configurations, weighted by their probabilities. Our experience of time flowing, of a definite past and an open future, arises from the particular way we are embedded in this timeless quantum state, from correlations between our memories and the state of the universe around us. This is deeply counterintuitive. How can time be an illusion when we experience it so directly? But consider an analogy. In a movie, all the frames exist simultaneously on the film or in the digital file. Yet when we watch the movie, we experience it as unfolding in time, with characters moving and plots developing. The flow we experience comes from the sequence in which we view the frames, not from any actual change in the film itself. Similarly, the timeless quantum state of the universe might contain all moments, all configurations. our conscious experience samples this state in a particular order, creating the illusion of time flowing. The before the Big Bang would not be a temporal before, but another aspect of the timeless quantum state, perhaps corresponding to highly improbable configurations or to different branches in the quantum superposition. Eastern philosophical traditions have long emphasized the timeless nature of ultimate reality. In Vedanta, a school of Hindu philosophy, Brahman, the ultimate reality, is described as beyond time and change, eternal in the sense of being outside of time rather than lasting through time. The world of time and change is Maya, illusion or appearance, a manifestation of Brahman, but not its ultimate nature. Buddhism teaches the concept of the eternal present, the idea that only this moment truly exists. The past is memory, the future is anticipation, but both are mental constructions. Reality is always now. Moreover, deep meditative states can alter the perception of time, leading to experiences described as timeless, where the usual sense of past, present, and future dissolves. These Eastern perspectives, developed through contemplative practice rather than mathematical physics, nevertheless resonate with some of the insights from modern cosmology and quantum mechanics. They suggest that our ordinary time-bound consciousness may not perceive reality in its deepest form, that there may be timeless awareness, timeless being, beyond or beneath the flow of temporal experience. Bringing these ideas together, we arrive at a conception of the universe that transcends time. The Big Bang is not the beginning of time in the sense of a first moment, but the boundary of time, the point where the temporal dimension ends or emerges. Before the Big Bang, there is timelessness, not an earlier time, but a different mode of being altogether. This timelessness might be the quantum state in the Hartle-Hawking proposal, the eternal inflation in a multiverse, the contracting phase before a bounce, or something we cannot yet conceptualize. In this view, the question, what existed before the Big Bang, transforms into what is the timeless ground from which time emerges, or what is the eternal reality of which our temporal universe is a manifestation. These are not questions about earlier events, but about deeper levels of reality, about the relationship between the timeless and the temporal, the eternal and the ephemeral. As you breathe slowly, imagine releasing your attachment to time, to the sense of past and future. Rest in the eternal present, this moment, which is all that truly exists in your direct experience. The past is memory, patterns in your brain. The future is imagination, anticipation. But this moment, this breath, this awareness is immediate and real. Now expand that presence beyond yourself, imagining the entire universe in this eternal now. All of space-time, from Big Bang to ultimate future, existing simultaneously in the timeless quantum state, in the block universe, in the mind of the cosmos. You are a part of this timeless whole, a pattern of awareness within the eternal structure, experiencing a journey through time that, from another perspective, simply is, always and forever. This timeless perspective does not diminish the reality of your experience. The journey through time is real for you, even if time itself is emergent or illusory from a deeper vantage point. The Big Bang happened, galaxies formed, life arose, consciousness emerged, you exist and experience. These are truths, even if they are truths within time, truths about the temporal aspect of a deeper, timeless reality. Rest in this contemplation, allowing the paradox of time and timelessness to coexist in your awareness without needing to resolve it. The universe is both temporal and eternal, both changing and unchanging, both beginning at the Big Bang and existing timelessly in the quantum state. These are not contradictions, but different aspects, different levels of description of the same ultimate mystery. We have traveled far together in this exploration, venturing from the familiar world of everyday experience into the strange realms of quantum mechanics and general relativity. From the observable universe to speculative multiverses, from the temporal to the timeless. We have encountered the Big Bang not as a simple explosion, but as a complex transition, perhaps from a quantum state, perhaps from a previous universe, perhaps from a timeless eternity into the flow of time. What have we learned? Not a definitive answer to what existed before the Big Bang, for such an answer may not yet be within our grasp, but rather an appreciation for the depth and beauty of the question itself. We have seen that before the Big Bang may be a meaningful question with various possible answers, or it may be a malformed question based on false assumptions about the nature of time. We have explored the possibility that the universe emerged from a quantum fluctuation, from nothing in a sense, though a nothing that contains the quantum fields and laws of physics necessary for such a fluctuation to occur. We have considered that our universe might be one bubble in an eternally inflating multiverse, where the Big Bang marks the birth of our local region, but not the beginning of everything. We have examined cyclic models where the Big Bang is a bounce or transition from a previous cosmic phase, suggesting an eternal universe without ultimate beginning or end. We have delved into string theory's vision of higher dimensions and branes, where our universe might be a three-dimensional membrane in a higher dimensional space, its Big Bang triggered by brane collisions or other exotic phenomena. We have encountered loop quantum gravity's picture of a quantized spacetime that might bounce rather than collapse to a singularity, replacing the Big Bang with a quantum transition. We have touched on the philosophical boundaries of what we can know, the limits of observation, and the questions that may lie beyond the reach of science. And we have contemplated the nature of time itself, seeing how it might be emergent rather than fundamental, how the block universe or timeless quantum state might contain all moments simultaneously, how Eastern philosophy and modern physics converge on notions of timeless awareness and eternal presence. Through all of this, a common thread emerges. The universe is far stranger, far more subtle, far more mysterious than we typically imagine. The comfortable categories of everyday thought, cause and effect, before and after, space and time, may be approximations that break down at the extremes. The ultimate nature of reality may be quantum, indeterminate, timeless, multidimensional, holographic, or something we have not yet conceived. This is humbling, but it is also inspiring. It means that reality has depths we have only begun to explore, that the human quest for understanding is far from over, that there are still fundamental mysteries awaiting discovery. The physicists and cosmologists working on these questions are engaged in one of humanity's great adventures, pushing the boundaries of knowledge, using mathematics and observation to explore realms that cannot be directly seen or touched. And yet, even as we push these boundaries, we must remember the value of uncertainty, of not knowing. The scientist and the mystic converge in their appreciation of mystery. The scientist knows that current theories are provisional, that new discoveries may overturn old certainties, that the universe continually surprises us. The mystic knows that ultimate reality transcends concepts and words, that direct experience reveals depths that cannot be fully captured in language or thought. There is wisdom in sitting with the question of what came before the Big Bang without demanding an immediate answer. There is value in contemplating the various possibilities, appreciating the elegance of each theory, recognizing the limits of each approach. This is not intellectual indulgence, but a form of meditation, a way of training the mind to hold complexity and uncertainty without anxiety, to appreciate beauty without needing to possess it. As you rest now, having journeyed through these cosmic landscapes of thought, allow yourself to feel a sense of wonder. The universe you inhabit, the body you occupy, the consciousness you embody, All of these arose from the Big Bang, from processes we are only beginning to understand. You are made of stardust, atoms forged in the hearts of ancient stars, scattered by supernovae, gathered into new stars and planets, organized into living systems, evolved over billions of years into a being capable of wondering about its own origins. This is remarkable. This is miraculous, even if the miracle is a natural process describable by physical law. The fact that the universe has brought forth observers, beings who can contemplate its vastness and probe its deepest secrets, is one of the great mysteries we have not addressed directly in this exploration. The origin of consciousness, of subjective experience, of the inner life of awareness, is in some ways as profound a mystery as the origin of the universe itself. Perhaps these mysteries are connected. Perhaps consciousness is not an accident, not a mere byproduct of physical processes, but somehow fundamental to the nature of reality. Some physicists and philosophers have suggested that consciousness must be included in our ultimate description of the universe, that the quantum measurement problem and the mystery of subjective experience are two aspects of a deeper puzzle. These are speculative ideas, far from mainstream physics, but they remind us that the questions we have explored about the origin of the universe and what came before the Big Bang are part of a larger tapestry of mysteries. We seek to understand not just where the universe came from, but what it is, what we are, why there is something rather than nothing, why that something includes beings like us who can ask such questions. The answers we have explored today offer various frameworks, various ways of thinking about these deep questions. They do not provide final, certain knowledge, but they provide paths of inquiry, ways of approaching the mystery with rigor and creativity. As our observations improve, as our theories develop, as new generations of scientists and thinkers engage with these questions, our understanding will deepen. But the mystery itself may never be entirely dispelled, and that is as it should be. For mystery is not the enemy of understanding, but its companion. Mystery invites us to explore, to question, to wonder. It keeps us humble, reminding us that we do not have all the answers, that reality is larger than our current conceptions. And it keeps us engaged, offering the promise that there is always more to discover, always deeper truths to uncover. So as we conclude this journey together, let us embrace both our knowledge and our ignorance, both the insights we have gained and the questions that remain. The Big Bang happened, of that we are confident. The universe expanded from a hot, dense state, cooled, formed structures, gave rise to stars and galaxies, and eventually to life. This is the scientific story, supported by overwhelming evidence. But what came before? Perhaps a quantum state, perhaps a previous universe, perhaps an eternally inflating multiverse, perhaps a timeless eternity from which time emerged. Or perhaps the question itself is flawed, based on assumptions that do not apply to the origin of space-time itself. We do not yet know. We may never know with certainty, but we can continue to explore, to theorize, to observe, to think deeply about these profound questions. And in that exploration, we honor the best of what it means to be human. We exercise our capacity for reason, for imagination, for wonder. We build on the work of countless thinkers who came before us, standing on the shoulders of giants to peer a little farther into the cosmic mystery. We participate in the great ongoing conversation about the nature of reality, adding our voices, our questions, our insights to the collective human endeavor to understand the universe and our place within it. As you move forward from this exploration, carry with you a sense of the vastness and mystery of existence. When you look up at the night sky, remember that you are seeing photons that have traveled for years or millions of years to reach your eyes, light from stars and galaxies born in the aftermath of the Big Bang. When you contemplate your own existence, Remember that you are the universe contemplating itself, matter arranged in such a way as to have awareness, to ask questions, to seek understanding. The question of what existed before the Big Bang is ultimately a question about origins, about beginnings, about the source of all that is. It is a question that may have many answers or no answer, that may be resolvable by future physics or forever beyond our grasp. But it is a worthy question, a profound question, a question that honors the depth of reality and the reach of human intellect and imagination. Rest now in the peace of not knowing, in the beauty of the question itself. Let your breathing slow, your mind quiet, your awareness expand to encompass the vastness we have explored together. From the quantum foam to the multiverse, from the timeless to the temporal, from the Big Bang to the eternal present, you have journeyed through ideas that stretch the limits of thought. And in this stretching, something opens, a sense of possibility, of wonder, of connection to the great mystery of being. You are here, now, conscious and aware, a participant in the cosmic story. Whatever came before the Big Bang, whatever lies beyond our current understanding, you are part of this unfolding, this eternal now, this magnificent and mysterious universe. Thank you for taking this journey. May you carry with you a sense of peace, of wonder, and of openness to the great mysteries that surround us. The universe is vast, strange, and beautiful beyond measure, and you are here to witness it, to contemplate it, to marvel at it. That is gift enough, miracle enough, answer enough, even as the questions continue to beckon us forward into ever deeper exploration of the nature of reality and our place within it.